All right, so we're coming back, and it's my pleasure to introduce Pierre Poulin, who will announce and introduce our first dissertation awardee. So take it away, Pierre.
Thanks. So it is my honor and privilege to introduce the winner of the 2019 Best Computer Graphics Dissertation Award well, I will simply call him Chaitanya because he has several names, but Chaitanya is the easiest and probably the most common for us. He completed his PhD degree at McGill under the supervision of the also simply called Derek, now Rosé Zarai. And Chaitanya started his PhD a long time ago when he was actually at the University of Montreal. So this is why we had to design a special committee this year of an anonymous evaluation committee for the thesis because I was in conflict. So, but fortunately, I'm very happy because I've been seeing Chaitanya defend his own thesis, and it was really a privilege. So, without any further ado, I will let Chaitanya take over and tell us about his great experience. Thank you, Chaitanya, and congratulations.
Okay, thank you. Is my voice audible?
Absolutely right.
Oh, okay. Thank you, Pierre. It is an honor to receive this award. I would like to thank my advisor, Derek, and all my collaborators for giving me the opportunity to work on diverse topics. I would also like to thank the selection committee, and last but not least, I would like to thank my family for their support. Let me share my screen. Oh, I think somebody has to give away the screen share for me to take over.
Try again now, please.
Okay.
Great.
All right. So can everyone see the screen? PowerPoint slide? Before I start, a couple of points. I'll take questions at the end of this talk, and I'll also provide links to the full videos which are there in this presentation. So let us start. Today, I'll talk about techniques to handle the challenges associated with high-dimensional integration problems, commonly found in wave propagation phenomena. Light transport is essential to simulate photorealistic images with global illumination. Global illumination synthesizes realistic images of virtual scenes by simulating the physical behavior of light propagation. It has applications in many fields, as shown here. These images are rendered using some of the commercially available solutions. What is light transport? Light sources emit particles called photons. Photons carry packets of light energy and travel in space, reflect at objects until they are absorbed. They might hit the camera, which records the light contribution. Photons travel along trajectories called light transport paths. And the goal of light transport algorithms is to capture the response of the camera due to all these light transport paths in the form of image pixels. Path integral formulation expresses the light transport problem as an integral over all light transport paths in a scene. Here, ij is the response of the camera for the jth pixel. The integration domain is over all light transport paths in a scene. And Fj is the measurement contribution function that determines light transported along a light transport path. Light transport algorithms use Monte Carlo integration to evaluate this integral for all image pixels. Standard integration techniques are impractical for such high-dimensional integrals. There are similarities between light and sound propagation. So far, we have seen how to render images by exploring the space of light transport paths. Now we look at how to simulate these acoustic effects. Here is a 2D illustration of a citadel scene, and A and B are two listener positions. We start a pulse source at a point, as shown on the left. Sound waves bounce and diffract around the geometry. They first reach listener point A, and then B, diffracting across the castle walls. Impulse response, shown on the right, records these acoustic wave interactions between the source and listener. We use numerical wave simulations to generate acoustic effects that span a multitude of propagation paths, as shown on the left. It is a high-dimensional problem, as both source and listener can move in 3D. And these simulations also involve a time-dependent impulse response results for each pair. In this dissertation, we examine the structure of high-dimensional space for both light and sound transport simulations. We propose new techniques to handle such high-dimensional integrations problems and provide significant improvements. Our first contribution investigates the high-dimensional structure of path space in the context of bidirectional path tracing. We propose a new path sampling approach that is much more robust to radiometrically complex scenes. Our second contribution exploits the large modeling capacity of deep neural networks to deal with high-dimensional integrals. We present a machine learning technique to address problems in image reconstruction. And our third contribution extends the light transport literature to solve problems in acoustic transfer. We develop an adaptive sampling method and a runtime interpolation technique for fast and efficient sound propagation. We briefly review each one of the contributions, starting with matrix bidirectional path tracing. Before diving into the details, we discuss a few path sampling strategies to generate light transport paths. We use this example scene with an area light source for illustration. We can generate a light transport path starting from the eye, compute the light contribution towards the pixel. We call this technique path tracing, and it can simulate various effects such as reflection, shadows, and global illumination. Another possibility is to start a light transport path from a light source. Light tracing can render caustics efficiently. Bidirectional approaches combine both the previous two techniques. We connect paths with all possible combinations between them. We made two observations with bidirectional path tracing. It samples and connects paths independently for each pixel. For example, we show two examples of pixels with a light transport length of 3. There is no spatial relationship between the subpoint endpoints across these two images as they were generated independently. Bidirectional path tracing does not exploit the benefits of stratified sampling. Consider a complex case as shown here. There is a light source in the adjacent room enclosed in a blue box. We generate subpaths as usual, starting from the eye and starting from the light. However, in this case, the light path does not contribute as it is in a difficult to reach scenario. But bidirectional path tracing still evaluates all possible combinations between them. Here, S and T represent the subpath vertices on the I and light subpaths respectively. We address these two issues with our matrix bidirectional path tracing approach. There are 3 stages in this process. We first generate subpaths starting from the eye and the camera, from the light, and then arrange these subpaths in the form of matrices based on their path length. We then reorder these subpaths within each submatrix to utilize the spatial relationship between them. And finally, we sample the matrix entries and connect subpaths and compute their contribution towards the pixel. Here are some results. This is a door scene commonly used in graphics research. There is a light source in the adjacent room. The top row shows the results for bidirectional path tracing, whereas the bottom row is for matrix bidirectional path tracing for an increasing number of sample count. Matrix bidirectional path tracing performs better than bidirectional path tracing as it can connect more subpaths due to its connection strategy. Matrix bidirectional path tracing targets offline rendering. It is challenging to render realistic images for applications such as games with existing path sampling approaches. We explore deep neural networks to address this problem. Path tracing is the de facto standard for rendering visual effects in games. It produces compelling results by sampling the space of light transport paths in a scene. Unfortunately, it can take much time to get a noise-free image, even on large render farms. Denoising is a set of techniques that take the noisy path trace image and approximate the converged image as close as possible. It is considered an offline problem. This example uses 256 samples per pixel, and the differences between the path traced image and the denoise results are subtle but important. I'll switch the slides. This is the denoised result, and this is the input path traced image. Notice even at 256 samples per pixel, there is noise across the walls and near the faucet. And this is the denoised result, which is able to remove them. Offline reconstruction solves a different set of challenges as the input already has significant information. It is not the case with real-time rendering. Games have recently migrated towards physically based shading, but we can only trace a few rays per pixel at 1080p and 30 Hz. A realistic sampling budget for games will remain on the order of 1 sample per pixel for the foreseeable future. And in this work, we are interested in the extreme case where we can only trace 1 sample per pixel interactively. We present a deep learning approach to reconstruct the final image. Here is the denoised result using our deep learning approach. I'll switch between the slides. At 1 sample per pixel, multicolor integration of indirect illumination leads to noisy images, so much that a lot of energy is concentrated in a small subset of pixels, as shown here in the instance. We frame the problem as a reconstruction of the final image rather than denoising. At extremely low sampling budgets, many image areas have only noise to begin with. We present a general reconstruction technique that significantly improves the state of the art in this regime. We propose a denoising autoencoder architecture for image reconstruction. First, we use encoder and decoder stages that increase and decrease the spatial resolutions. Then we link the encoder and decoder stages through skip connections to recover the lost information. And finally, we add recurrent connections to retain information across frames for temporal stability. We train the network by mapping input sequences with desired target sequences. We compare our results with a machine learning-based filter that was the state of the art in denoising at the time. We term it as learning-based filter. And here are the results. This is a San Miguel scene, and the input is very noisy. Learning-based filter was trained on 20 scenes using a wide range of multicolor effects. Our network can preserve features such as reflections, shadows, and global illumination. It can achieve temporal stability, which is usually very challenging for extremely low sampling budgets. Our previous two contributions gave us insights on path sampling and reconstruction techniques for light transport simulation. We leveraged this knowledge and used path tracing to develop an adaptive sampling method for interactive sound propagation. Games and virtual reality applications require global propagation effects to create believable virtual worlds. Sound propagation effects provide important perceptual cues in order to navigate in and around the scenes. These oral cues are essential to immerse the listener and provide a convincing experience. We use pre-computed systems to perform the expensive transport simulation offline at a few sampled set of probe locations, shown here as blue boxes. At runtime, the acoustic parameters from these probes are interpolated to the player. Here is a demo of one such system. The sound source is the church. Notice sudden sound changes when the player enters the tunnel and the cathedral, as there are no probes available in this location. Pre-computed systems often use uniform sampling of probes and visibility-based interpolation. We discuss a few issues with these approaches through illustrations. On the right, we visualize the top view of a citadel scene. Blue dots represent probe samples, and the red dot indicates a potential player location. Uniform sampling can miss regions such as narrow corridors or tunnels. For example, there are no probes available or visible to the player location as shown here. They might also fall inside the geometry. In order to overcome such issues, we have to increase the sampling density of probes. However, this is not practical due to the pre-computation and memory requirements. We visualize the top view of a house scene. At runtime, pre-computed probe information must be interpolated to the player location. Probes invisible to the listener are often rejected, which introduces artificial jumps at visibility transitions, shown here by the red or the orange dotted line. Human auditory perception is sensitive to abrupt loudness changes on slight player motion, breaking immersion experience in VR. We address these issues with our adaptive sampling method. Here is a demo of our system. Notice the gradual transition when the player enters the cathedral. We emphasize that we do not use more probes, but rather place them better when compared to the uniform sampling technique. There are three main components in this system. First, we use a local diameter measure to enable scene adaptive sampling. This local diameter measure captures the notion of a scene spatialness or narrowness around a given point. And we build this diameter measure using path tracing technique. Then we use this measure to vary the sampling resolution and eliminate undersampling in narrow regions. And we achieve smooth acoustic effects through a runtime interpolation technique based on a radial weighing scheme that uses geodesic patterns. Narrow tunnels and corridors are common in large game scenes, such as Citadel. And uniform sampling can miss such regions entirely, as shown here. Our technique adapts resolution locally to sample such regions. In this dissertation, we examine the high-dimensional space for both light and sound transport paths. We propose new techniques in rendering, reconstruction, and sampling for realistic visual and oral effects. We provide significant improvements for both offline and real-time rendering contexts. We introduce a new rendering algorithm that performs stratification in connection space by utilizing the spatial relationship between subpath vertices. We present a machine learning technique to reconstruct a sequence of Monte Carlo images at interactive rates for extremely low sampling budgets. And finally, we develop an adaptive sampling technique to capture acoustic effects for narrow thin features within a practical budget of pre-compute and runtime memory. Thank you.
Thank you very much. Our attendees, please use the Q&A button below to ask your question or raise your hand using the participants tab, and I'll unmute you and call on you. Chaitanya, maybe I'll start with one question. Something I was really impressed with the autoencoder that you contain in your thesis. One thing that I've been wondering about is, the test scenes always have these like really fantastic caustics and like interesting phenomena that are really, really difficult cases for rendering. I guess like an average scene will have maybe a mixture of these. Like some objects will be really easy to render, whereas others will cause really interesting light events. Do I understand correctly that the flow through your algorithm is sort of the same for every pixel, like collecting a few samples and then running the autoencoder?
Yeah.
And if so, is there a way that you could leverage machine learning to determine where to best spend a budget?
Yes, a couple of things. Can you hear me?
Yes.
Oh, okay. So for this technique, we initially concentrated on like generic effects such as reflections, shadows, and limited ourselves to one bounds indirect. So that means effects such as caustics or any advanced effects weren't considered. So we designed our autoencoder architecture based on these assumptions. Of course, it is possible to expand this to include advanced effects, but that comes at the expense of how much time we would need to generate these kind of data sets beforehand, because usually caustics and other advanced effects take a lot of time. But it is possible to generate some kind of an important sampling criteria where we might tell the autoencoder to concentrate more on a particular set of effects. But in our work, we did not look beyond the generic effects.
Since I'm not able to raise my hand, I'll do the proper hand raising here. So thank you, Chaitanya, for the great presentation. Another question about the denoising. I mean, basically, you're trying to get some level of temporal coherency. So, but if you have some small motions like wind that would make some of the shadowing move on the on different location, would it be possible to differentiate with deep learning those small details when it is temporal currency and when it is due to basically small motion or effects from small motions?
It might be possible. For example, when we are doing these temporal aspects of the autoencoder architecture, we consider how information is retained across frames. So that's essentially what we do in our architecture. We are using something called recurrent convolutional blocks, but we give a sequence of 7 frames to capture enough information across these different frames. So in our experiments, we were able to gather information about illumination and about different high frequency effects, which we were able to eliminate, which are usually very difficult with traditional temporal anti-aliasing techniques. Of course, it's a question whether we can do the same thing with the example use cases you mentioned about shadows from a wind or other things. We haven't tested that. It also depends on whether the data set includes those kind of effects. And if we show the network or the autoencoder architecture these kind of data sets, it might be possible to replicate them and still achieve temporal stability for those kind of things.
Thank you.
We do have one question for the audience, so I'm going to try to unmute them now. Prashant Raina. Might take a second.
By the way, I just posted the full video links on the chat. So if
oh, excellent. Thank you very much.
If someone is interested, they can have a look at it.
Prashant?
Hello, can you hear me?
Yes.
Yes.
So my question is, I've used NVIDIA optics before, and I've seen the AI denoising. It's really impressive. And I was wondering, how did you avoid overfitting to the environments that were there in your training data? And you even have a recurrent component in your neural network, which means there's a risk of overfitting to the sequences that were in your training data. So
yes.
How did you get something which can be used as like a general product for anyone?
So there are a couple of aspects to that. One is we try to include generic effects in our data sets, such as shadows, reflections, and global illumination for generic scenes, which are extendable to most of the game scenes used these days. Of course, we haven't tried to expand it to advanced effects, and we try to just simulate the autoencoder architecture training for these data sets. And we observed that we were able to extend it well to scenes which were not shown to the autoencoder architecture. For example, we never showed the San Miguel scene to the autoencoder architecture. It has high frequency features such as vegetation and other effects. So in that sense, we were able to train the autoencoder architecture to be generic enough. Of course, we still were able to see some artifacts for like very glossy or specular reflections where the network didn't come across those kind of features earlier. So it used to blur out during those kind of scenarios. And the second aspect is that it might be possible just to use the autoencoder architecture for a very particular game scene. And typically, that's a common use case scenario in games where you might have a game level for each, you might have a scene for each game, and then you might actually want to train your network just for that scene so that it could perform really well for all the effects it can see for that particular scene. Of course, it will not be robust to include effects and to denoise other scenes which were not included. So these are a couple of scenarios where you could try to avoid overfitting for the architectures we have used.
Great. We have another question from one of our panelists, Paul Cry. Paul, want to jump in?
Yeah, can you hear me all right?
Yes.
So, Chaitanya, amazing stuff. I'm not sure you really. I mean, I guess what I want to say is that the denoising and the acoustics work is has wide applicability, right? And I believe it's actually getting wide use right now. And I wonder if you even have an idea of just how wide each of these techniques are used. Maybe you can comment on what you know about that.
Yes, so I can tell how they're currently being used in the industry. So the work which I did, so both of these works, denoising and acoustics work, I did with NVIDIA and Microsoft as a research intern. So at NVIDIA, our work was incorporated into optics path tracer engine, and right now it is being used in the industry like Hollywood movies to try to cut down the render times for denoising. Usually to render a frame, they take like a day or so. So with these denoising approaches, they are trying to cut down those kind of rendering times and increase productivity. And with acoustics, our work is integrated into Project Acoustics. That's part of Microsoft's effort for developing real-time sound propagation techniques. And this is currently being used in a lot of games and virtual reality applications, such as Gears of War 4 uses this technique. And my component is part of that framework. So in that sense, it has a wide applicability in the industry, and I have to say that I've been very fortunate to work on these two varying topics.
All right. Well, let's all thank Chaitanya again, and congratulations for the award.
Thank you. It has been a really great honor to receive this award and be associated with it. Thank you.
Congratulations.